Okay, so first of all, the announcement that I already made in Russian, if you want to get the credit for this course, please send me an email. I'm going to add you to the Google Plus. So in the Google Plus, I'm going to post assignments, which is the only source for the marking this course. Okay, so let's start the second chapter. So I hope I can finish this chapter today.
I'm sorry, how should we write to what is the address?
Well, you can send an email to official email address of the university.
We should write from the Gmail.
Yeah, please send the email from the Gmail because we have Gmail for the Google Plus. Okay, so chapter 2, I'm going to call this Verdier localizations. So the problem we're going to solve in this chapter is the following. Suppose I'm going to change notation a little bit. My basic category will be D. So D is the related category. And since this related category has some related subcategory C, so this is also related subcategory. So this is given. So I want to construct the quotient of the D by C. So this is the goal essentially of today's lecture. So what's the quotient? The quotient actually it's can be pair. You have a new category D mod C, which is exactly Verdier quotient or Verdier localization. Quotient of localization. And also there will be a functor which I'm going to call in this chapter Q. So this is just a triangulated functor. So Q is triangulated functor. And this diagram, so this pair Q and D mod C has the universal property. So the universal property is the following. If I have any other triangulated category, so T is any other triangulated category, and the functor from the D to C. So, so we have this pair. So pair Q D mod C has universal property. Which is the following. For any triangulated category T and functor, triangulated functor of course, triangulated functor, let's say this is F, from the D to T, so this is this functor on the diagram. So from this functor I want to require so triangulated functor such that C is in the kernel of this triangulated functor. So for any such other functor F,
What do you mean by kernel? What do you mean by kernel?
well, the kernel, so this is full subcategory of D with objects X such that F of X is equal to 0. So if this is additive category, right, so there's a 0 object in this category, then you have a functor with additive categories, you can define notion of a kernel this way. Right, so
This should be equal to isomorphic
what do you mean?
to 0.
Well, isomorphic, of course, yes. Isomorphic, yeah. Just a lazy way to say isomorphic. Yes. Sorry.
Is C full subcategory?
By my definition of triangulated subcategory, C is full. Because I define triangulated categories in such a way that they are full with additional properties. Yeah, so for any such diagram, well, you can find the unique functor. So there is a unique factorization of, so maybe let's call this F with a tilde. So there is unique F tilde on the quotient category for T, not such that the diagram is commutative. Diagram is commutative. So that's the problem we want to solve. So that's essentially the goal. And we're going to do this kind of step by step. Well, I'm going to define D mod C. I'm going to define, first of all, I want to show that this is a category. There is a fundamental problem with this whole construction, is that if you start with the D, which is kind of the category of what we usually call the category, meaning that the home form are sets. It is not necessarily true that when you form this quotient, this property is too satisfied. So it is possible that in this quotient category, the homes are just classes. So in this sense, this D mod C is not necessarily what is called locally small. Locally small means that the homes form sets. And even in the applications, for example, if you start with some reasonable abelian category, you take the derived category of this abelian category, it's not necessarily true that homes form sets. So essentially, one of the theorems that we're going to prove, an important theorem in this course, probably one of the most interesting and technical results in this course, if you have a Grothendieck abelian category, then the derived category have small sets, meaning that sets are home spaces are sets. So it's not an easy thing to show. We will try to do this maybe in November. But at the moment, we keep in mind that D mod C is not necessarily locally small.
Excuse me, why it's sometimes called localization?
Well, I think that depends how you think about this. In the category, you have maps, right? And you have objects. What we are going to see, well, kind of, it's not exactly true, but you want to
see that the morphism is looks like localized.
Yeah, so I want to say that there are two ways to think about the quotient. First of all, you want to kind of say that objects in the C, you want to kind of say that they are all zero. So in this sense, this reminds the quotient. On the other hand, you can say that all the morphisms with what I call morph C in this category become isomorphisms. And this is how the localization looks, for example, in the commutative algebra. So in this sense, kind of in the category theory, you can call this quotient, you can call this localization, depending how what you think is more important, the maps or objects. Okay. So yeah, the plan is to do this step by step. I want to show that this is the category, not necessarily locally small, then I'm going to show that this is additive, and then I need to show this is triangulated, meaning that I need to check all the axioms. Of course, the first three is trivial, the other two is a little bit harder, but I'm going to leave this as an exercise, because it's actually quite terrible to check the TR4 in the D mod C on the blackboard. But it's kind of useful when you do this yourself for the first time. Okay, so let's define this category. Kind of start with objects. So the objects in the quotient D mod C are by definition the same as objects in the category D. So the objects are the same always. But the maps are different. So if I want to take a map, say in the X to the Y, but in the category D mod C, so such map is represented by the diagram, which is usually called roof. By the diagram. So let me draw a diagram. So it's the following. You have X, Y, and then you have another object Z, and there are two maps, F from Z to X and map G from Z to Y. So in this diagram, I always assume that this first morphism, F, is in the morph C. Of course, objects that we see on the diagram are all objects in the D. So any map is represented by such diagram, where F is in the more C. And by the way I draw this diagram, it is you can see why sometimes these diagrams are called roofs. So diagrams which are also called roofs. Okay, but on this kind, and you can already see that why there's a problem with the D mod C being locally small. Well, because I can choose this even between two objects. I have the sets, the homes that are sets. I can choose this object Z, and then for this object Z, I have kind of not a set but a class, right? So objects form just a class, not necessarily a set. Okay, so on these diagrams, I want to introduce the equivalence relation, and then I'm going to say that the quotient class is the home in the quotient category. So the equivalence relation is the following. Suppose I have.
Excuse me. Am I understand right that this is just a diagram such that only F lies in more C?
Yes.
And what about J?
J is any mat in the category D. So essentially the idea is you want in the quotient category you want to invert all the F's. If you write an arrow kind in this direction, you can essentially think about this that you work with such a fraction. So in particular for the F there is an inverse. So if you draw such diagrams, we inverted all the morphisms. I'm going to prove this.
And why? We will prove.
Yeah, I'll prove everything with more details later. At the moment, I'm just explaining the idea. So I want to introduce the equivalence relation on these diagrams. So if I have one such diagram and another such diagrams where I have Z prime, F prime, and G prime, so they are equivalent if there is another roof. So just for save some space, I'm going to draw this in one line. So say Z double prime, F double prime, X and Y. So there is a roof and maps. Maps say U from the Z double prime to the Z, and map V from the Z double prime to the Z prime. Well, such that I have a commutative diagram. Such that the following diagram commutes. And here's the diagram. So I have three triangles. X in the middle, I'm going to draw double prime. And then on the top there will be a roof with the Z prime. So this is F prime, G prime, so F double prime, G double prime, finally Z, and G. And the maps that exist are here. So this first map is what is V, and the bottom of map is V. Okay, so this diagram is supposed to be commutative. So all the triangles, quadriangles that you see here are commutative triangles. Yeah, and of course when I say that this is the roof, it means that I have this the two maps, an object in the middle, but this first map, when I say this roof, means always in the more C. So F double prime is in the more C. So about this diagram I have couple of remarks. So first,
U is in.
yeah, this is the first remark. So the first remark is that the maps that we have, we can require that they are in the more C, but in fact this follows automatically. So these two maps are in the more C. Well, for example, look at this triangle, right? In this triangle, I know that F prime and F double prime is in the more C, and F double prime is the composition of the V and F prime. But last time we proved the property 2 out of 3 for the more C. If for 3 maps two maps and their composition, 2 is in more C, then the third is in the more C. So V is in the more C, and for you the argument is exactly the same. And second remark, this is not really a precise mathematical statement, but it's kind of analogy. So what this diagram represents? It represents that you, as I promised, you work with the rooks as kind of fractions, and this diagram means that you can kind of do the standard computations with the fractions. For example, this is kind of formal computation, so in quotes. I'm going to do this in a formal way a little bit later. Well, not this computation, but make sense of these fractions in a formal way later. So the first, I can write formula like this, and right, so you inverse is just the identity, and then you can simplify this to the G double prime in the F double prime inverse, and then also obviously insert V and V inverse in the middle. So you can see that kind of you can go from there are primes here, everywhere, here, and here. You can kind of go from one fraction to another fraction by doing the standard computations with the fractions. So that's the meaning of this equivalence equation. And the exercise, which is just an exercise in category theory, check.
There shouldn't be -1 with G prime.
Where?
It's the last one.
This is G prime.
Yeah, there shouldn't be -1. We
Oh,
can't.
yeah, thank you. Yeah.
We can't reverse G prime.
So check that this tilde is indeed an equivalence solution. It's kind of a little bit long, maybe a range of computations, but it is useful when you see these rules for the first time. Okay. So some details which I think easy to show, but just a little bit long, I'm going to leave an exercises in this lecture. So if I say that this is a morphism, I need to define the compositions of morphisms. So let's define composition of two rules. Composition. Maybe let me say composition of rules. So let's take.
Excuse me. Can you please? I don't understand. Can you please explain what does it mean to F to lie morphisms in C?
That is because probably missed the previous lecture. I defined, maybe I'll write it here. So whenever I have a triangulated category, this D, sorry. So if D is triangulated category and C is a subcategory, I defined more C. This is just a kind of class of maps in the category D. So these are maps F in the Hom D X Y, such that I have a property whenever I have a map F from X to Y, I can complete this map to a triangle. And in unique up to isomorphism way. So there is also Z and there is X shifted by 1. So then the requirement is that this object Z is in the subcategory C. This kind of definition of force C.
Thank you.
So you see the kind of equivalently, as I was mentioned before, you can think in the quotient category, you're killing all the Z's that are in the C. If they put 0 here, it means that F becoming an isomorphism. Or you can say this is an isomorphism, then it means that Z is kind of 0 in the quotient category. That's the idea behind this definition of morph C. Okay, so let's compose two rules. Okay, so I think I have enough space here. So suppose I have first roof with the, say, W1. This represents a map from the X to the Y. So I'm going to call maps F1 and G1. And another roof, which is representing a map from Y to Z. So vertex will be W2. So I find it a little bit easier to draw maps in this way, not just as the roofs as I draw it in the beginning, but kind of rotate them by some angle. So, okay, so this is a given, right? So this is a roof that gives a morphism from X to Y in the quotient category. This is a roof that gives a morphism from Y to Z in the quotient category. So if I want a roof that can give a map from X to the Z, well, what we need is kind of write this W3, find two maps, right? And there is in the triangulated situation, there is a kind of easy way to do this. We can take this to be homotopy pullback. So this square that we have here, we can say that this is homotopy pullback.
Yeah, but we didn't prove that after homotopy pullback, F3 will be in morphism C.
Yes, we did.
We did.
Yes.
Because an exercise
Maybe I left this as an exercise, but if I left this as an exercise, it's quite easy. So for the homotopy Cartesian square in the triangulated category, I think we proved this, that if this morphism, so this morphism is in the morph C,
yes.
even only if this morphism is morph C. So this map, actually I call this V and U, like, well, I don't know, that doesn't really matter how to call them. Maybe. So this is of course F2, maybe F3. So by the property of the homotopy pullback, F3 is in the morph C. So that's the definition. And what's nice about the homotopy pullback, well, we'll always know that there is one intermediate category. So this is not unique, it's only unique up to isomorphism, but anyway, this makes sense that this definition works. And immediately, we can improve this definition a little bit. I have a lemma that says that it's not necessary to take homotopy pullback. Actually, any diagram is such that this composition, well, this map V prime, this map F3 is in the morphisms, will work as a composition. So more precisely, given a diagram, as we want, so let me call this object P. So the diagram is the same as before, but not with the homotopy pullback, but with some object P. So, given a diagram, let me write it here.
Answer the question.
Such that, just let me finish them. So V prime is in the morph C. Yeah.
You know that homotopy pullbacks exist because we just take the cone of the map on the direct side, right?
Yeah. So if you have this part of the diagram, let's give you a map from the sum to the y, and you complete this to the triangle, but kind of in the other direction. So given such diagram with the property that V prime is in the morph C, the conclusion is that it agrees with composition, meaning that this is the same diagram modulo equivalence relation. Equivalent to composition. Okay.
So I don't understand.
I'm just saying, well, in the definition of the composition, I take two rows for a composition. I take a homotopy pullback here, right? Now I'm saying that I can write any square here just with the property that V prime is in the morph C, and any such diagram is a composition.
So the lemma is that such diagram is equivalent to the standard composition as well.
Yeah. You can take a diagram with push out, you can take any diagram with A and B prime in the morph C, and these two diagrams are equivalent modulo equivalence relation. And that's what we need to show, and in fact that the proof is just one diagram. So let me maybe rewrite this diagram again that we have before, that we used in the definition. Yeah, and for this diagram, have object P, right? So then we have maps which are called mu prime, and there is a map mu prime. Then I know that there is a map, exists a map here such that these two mu triangles, so namely this one and this one, are commutative. Right? This we know by the properties of the homotopy pullback that I proved last time, showed last time. It's a very easy property. F1, F2. But now,
This by definition of pullback, but you need also to be homotopy. And what we say about V prime and U prime?
no, V prime and U prime are here there. And this is not by definition of a pullback, but this is by the property of homotopy pullback. So last time I proved that if you have a homotopy pullback, there is a map like this. It's not unique, but there is a map.
Not okay.
So that was the kind of downside of the homotopy pullback. Okay. But now, this is precisely the diagram which you have in the equivalence relation, right? In the equivalence relation, you have kind of three parts: the top part, the middle part, and the bottom part. But in this case, you can think about this as the two parts inside. So kind of the generation of that equivalence relation is just have two triangles and a map between the objects in the center. That's what I have here, right? We have two objects, two triangles, and the map, two groups, and the map between the objects in the center of those groups. So that's the proof.
And we know that this map is from morphism C by the property that we proved last time. Yeah, because V
Yeah.
and prime are from morphism C.
Yeah, well, yeah. Again, this is two out of three property. This is two maps. The composition is more C. This is more C. So this is more C. Yeah. Okay. Another exercises. So exercise 1 is to check that the composition consistent with equivalence relation. And second part of this exercise is to show that the composition is associated. I'm going to add some of these exercises in the first problem set.
Excuse me. We should look that these two diagrams are equivalent, but for the equivalence we need some third object.
I was explaining you can take, for example, map V or map U in the definition of equivalence to be just identity.
And we take P as a third object. We take P as a third.
Well, it doesn't really matter. You can take either P or W3.
No, we have map from P to W3, but not have map from W3 to P. So we take P in the center as W prime.
Yeah, we can do this. Yes.
Okay.
Okay, so this is the lemma. Now I give a definition. Now we can also define the functor Q. So this is functor from D to the quotient category. So this functor is identity on objects. For objects this is easy, objects are the same. And if I want to apply this functor to a map, let me present this map as a diagram. So map from X to Y. So by definition, I say that this is a roof where I have X, Y. So the first map that's supposed to be from more C is just the identity map, and the second map is F. So that's the definition. I don't remember, maybe I did this last time, maybe not, but there is an easy remark that any isomorphism is in more C, always. Yeah, that is because in the additive category there isn't zero object. Okay, so lemma. It says the following, that it says that if I take, okay, let me just formulate it, don't waste time to explaining this another way. So we have a map from X to Y in the category D, and this map is in the more C. So then, in the quotient category, this map is invertible, so X, F, Y, 1, X is invertible, and moreover there is a precise formula for the inverse of this map. This is kind of the transposition of this diagram, that the inverse of this map. So we see that with this definition, one of the properties that we want is that every map in the more C become invertible is actually satisfied by this lemma. Okay, the proof is kind of very easy computation of the two compositions. So for example, let me compose this in the one way. Right, so one way to compose them would be something like this, right? So take composition in one order. So then I know that any square works. So let me write in this square, so any square with the property that this map is in the more C. So let me just write this x, 1, 1. So this is clearly satisfying the requirements. And now if I take the composition, and this is clearly the x, 1, x, 1. Well, I didn't say this, but of course, maybe I need to say it somewhere, that the identity from x to x in the D mod C, which of course represented by the diagram, is represented with the x, 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 and two maps are just the identities.
Well, it's kind of obvious from our definition of.
Yeah, we'll just say this precisely. So the composition in one order is just the identity on the x, and the composition of in the other order, yeah, I think it's even simpler. So let's check this. So in the other order, I would have x, here f, the x, and this is an engine. Right? Yeah, that's right. So here we have 1, f, x. And the same thing works, right? So the same thing works, I can just add another x with the two identity maps.
But there should be y in the left corner and right corner.
Yeah, thank you. Yeah, wait, but there's also y here, right? So here we see the diagram, which is x, f, y, y, which at the moment looks like not a correct answer. But it is a correct answer because I can look at the following diagram. So I have x, f, f, y, y. So here I have y, 1, 1. And here there is a map f, and I know that f is in the more C, so this is commutative, and this is the, again, equivalence relation where one of the maps is the identity and the other map, u or v, is just f. So this is, by this diagram, this is equivalent to the y, 1, y, end of the problem.
And there is a similar computation, which is done by the same method for composing proofs. So let me give this as another exercise. So that if you have now any roof, so with a say vertex W, map G, and map F, so that you can always decompose this into a composition of two maps. W, G, Y as before, but now this is the map which is identity on the W, and the other proof is that W identity map to the W and F which is mapped to the X. So there's always such a decomposition, and the proof is more or less the same. You just take these two diagrams to calculate the composition. I don't want to do this again, but what we can say from this exercise is that so by exercise so by exercise, maps in the D mod C are of the form Q of G, composition with the Q of F inverse. Right, because this map that I have here is precisely the inverse of the Q of F inverse by the lemma that I proved before, and this composition is by this exercise. So what we see is actually a way to present any map as a fraction, and this is now a correct way to do this. If you just write it like this with the previous two computations, this works. So finally, we can summarize everything that we proved so far and say that we have a theorem. So the functor, I don't know this triangulated functor, this is just a functor between categories. So functor Q from D to D mod C is universal for all functors F from G to some category T. Now I'm going to continue to call this T, but at the moment T is not triangulated, just a category, which takes all maps in more C to isomorphisms.
So if you prove that it is triangulated, then make sure it gets more than we asked for.
At the moment, I don't say anything about triangulated, so I just at the moment I just know that this is a category which is not necessarily locally small. That's all I know. So the next step would be to show that this is additive, and the next step will be to show that this is triangulated.
And again, about local smallity, we don't know that it is local. We don't know that this.
It is just not true in the whole. I wasn't here in the beginning, but I made the remark that even if you take an abelian category, take a derived category, it's not necessarily locally small. Okay.
And when we even want it to be locally small?
Because the definition of category
You
has to be
can
locally small.
take at least.
Okay, thank you. I actually wanted this.
Yeah, why?
Because in the definition of category, categories are locally small usually. Like the one that, for example, was told in the previous story in the class in category.
No, well, that is a kind of precise technical reason in this course why we care about this. One of the key theorems that we're going to use to say that there is an F with the upper cross is Brown representability theorem. And in this theorem, you need that the two categories that you have functor between these two triangulated categories, which are locally small. And then for functor there is a right adjoint. If this functor preserves coproducts.
So we'll get a condition when the quotient is locally small.
Yes. One of the important theorems in this course will be that if you have a Grothendieck abelian category, then the derived category is locally small. Okay, so do we really need to prove this? I want to say that the proof is clear. It just follows from everything we've done before. Right? Why this is clear? Because if you have this functor, right, that maps all the maps in the more C to the isomorphisms, you can immediately extend this. Well, objects are the same in the quotient. You can extend this F on the objects in the D mod C immediately, but on the maps you can also do this immediately, right? Because you already know that if you apply such functor to a roof, right, and the map is in the more C, this is mapped to the isomorphism, and this formula makes sense for the isomorphism. So there is clearly an extension to the D mod C, and if you think about this a little bit, you realize that this is the unique extension. Okay. And from this theorem, I want to make one important remark.
So you can consider two pairs. You can take the opposite category of D, which is again triangulated, and then you have a functor, an opposite functor between opposite categories, so D mod C opposite. Or you can consider opposite category and take a quotient of the opposite category by the opposite subcategory. And by the previous theorem, they have the same universal property. So then I have a diagram like this. So I'm kind of taking the opposite, commutes with taking the quotient.
Understand why is there a map from left to right by universal property? Why is there a map from right to left?
Again, by the universal property. So that both categories satisfy the universal property. So the object with the universal property is unique.
And this way we have equivalence.
Yes. By uniqueness of the universal object. So we have this kind of equivalence of categories, and the important observation is the following. Representing map from X, Y in the D mod C by our standard roof, so say Z, Y, some map alpha, X, and this alpha is in the more C. So if we invert all the arrows, then this represents the map X to the Y and the D opposite modulo C opposite, or by what we just showed, a map from Y to the X in the D mod C. So the upshot is morphisms in the home D mod C XY can be also represented by the roofs, but of the other kind. Sometimes this is called the left roofs and the right roofs, but I don't really want to always remember what's left, what's right. So I have a roof like this, but now alpha is in the more C. So, or by fractions,
I think we should write opposite somewhere in the home DC.
here? No. So because this is the argument.
I'm starting with the roof, right? I'm presenting like this roof map in the opposite category, then I'm going from the opposite category to the original category. That would be a map now from the y to the x. And now if I as a map from y to the x, this is precisely of the structure.
So, or as fraction, say q of alpha inverse q of beta. So the upshot is that these two theorems are equivalent. So we require one sort of proofs where one map is in the morph C, but you can do this in the other way, in the other order. You can start with some map and then you kind of map in the other direction, which is in the morph C. And the two theories are equivalent by the universal property. So we can use, maybe we can call this left fractions, and what was before we can call right fractions, and the two calculus of fractions are equivalent in this case. And this remark is not just kind of general remark, it will be important for one computation. Kind of in one of the proofs it will be important that we work in these fractions. Okay. Another lemma. Quite useful, and we're going to use this a lot later. So let F and G be two maps in the category D. So be maps in D. So then the following are equivalent. Three conditions. So first condition is that after localization, they give the same map. So Q of F is equal to the Q of G. So the second condition is that there is a map alpha. So this is a map in the D and also in the morph C. So there is a map alpha such that if I take a composition with alpha, then the maps are the same in the D. And the third condition is that the map F minus G, I'm using that I have additive categories, so it makes sense to take the difference of two morphisms. So this map factors through X, through object C, which is in the category C.
May I ask for questions? So there we had alpha in morphism C. And after and then we say can be also represented by such diagram, and already alpha in morph C, but alpha goes from Y to Z. Not from
This
X.
is exactly what we have in this diagram, because this, in the category D1C, this represents a map from the Y to the X.
Yeah, but there's map in morphism C goes from X to Z. And there's map from the morphisms of C goes from Y to Z.
Yes, so what's the problem?
Yeah. Yeah, okay.
This kind of for any morphism, right?
Yeah, I understand.
So and now I'm going to erase this. Okay.
Excuse me, C. What does it mean, factor in C?
Well, it means that this F minus G, you can kind of write this, find another two maps. Yeah, so there are two maps here such that the composition is F minus G.
Okay, so first I'm going to prove that one is equivalent to two. So condition Q of F is the same as the Q of G. If I just kind of go back to the definition of the Q, it means that this roof is equivalent to this roof. Or what it means to have an equivalence, it means that I have the following commutative diagram. So X, there is some object W in the middle, y, x, so here f1, f, x, here this is 1, this is g, and there are maps here and here. So this map, let's call the map that I have from W to the X, let's call this alpha, right? But then immediately we see that if this is alpha, then this has to be alpha, right? Because we have just one here. And from this triangle, if this is alpha, this is the identity, this map also has to be alpha. So three maps coincide in this diagram. Right? And that's all I need, right, in the condition 2. I have a map alpha in the more C such that this triangle is commutative. Right, so I take a position of the alpha and F, this is going to be this arrow, take a position of the alpha and G, the same arrow, so they equal. And conversely, of course, if I maybe instead of writing 4, I can say this equivalent, right, which is equivalent to condition 2. You have map alpha such that these two squares are commutative. Of course, these two squares will be automatically commutative, so these two proofs are equivalent. So this is the proof that 2 is equivalent to 1. Okay. Let me see, maybe I'll try to squeeze here the proof that 2 implies 3. Okay, so now I have this map alpha. I want to show that these factors, but the condition that f alpha is equal to the g alpha, I can write a little bit differently that f minus g composition with alpha is equal to 0. Okay, now I look at a distinguished triangle. Take W, take map alpha to the x. So complete these two distinguished triangles. So there is an object C, and then there is the shift of the W. So here, since I know that alpha is the more C, I can say that this object C is in the category C. Now, to this distinguished triangle, I want to apply cosmological functor. So apply hom into object Y. So then I get the following exact sequence. I have hom between C and Y, which is mapped to the hom between X and Y. Right, so this is called a variant functor. And finally, this will be hom W Y. Now, here lives the map F minus G. This is the element in the middle of hom. And of course, the maps in the homes are just induced by the composition. And so here, if you want to go here, this is just the composition with alpha. So this is sent to the F minus G composition with alpha, which is 0. By the exactness, I can say that there is some map T, which is a map from C to the Y, which is sent by the composition with some map X to the C to the F minus G. But that's exactly the existence of localization. Right, so this map F minus G, well, let me call this second map, say, beta, right? So then F minus G is the composition of the T and beta, right? So beta is a map from the X to the C, and T is a map from the C to the Y. So factors to object in the category C. Okay. Maybe I erase this part. So finally, the last part is that 3 implies 2. Okay, so
if I have such factorization, so f minus g can be factored as the x, c, and y. So I take a map x to the c and complete this to a distinguished triangle. But I'm going to call this object, the third object, w shifted by 1. Shifting by 1 is autoequivalence. I can call it whatever I want. I can call it some w prime, but it's in fact a shift of some object w. So then there will be a map from the x shifted by 1. And why I'm doing this? Because I want to call this third map alpha shifted by 1. Right? So if this factors, I have such diagram, right? And complete this to a distinguished triangle. And so I want to show that there is an alpha. So this is the alpha, right? So I can shift everything back by 1. So that's a map from the w to the x. And if I So I want to say that if I take a composition of the f minus g with the alpha, right, so then I'll get 0. That's what I need to show. So I think again I can take the apply home. So do the same computation, apply home into the y, to this distinguished triangle. So
I think it just follows from the fact that composition of two consequent arrows is 0. We can.
Yeah, we know that beta. So we know that w to the c is 0, and what's
w to the c.
Yeah, that's true. What's
Oh, we know that
what's
this composition is 0, right?
c to the x shifted by 1 is 0. Yeah. So what?
Well, I think I need to apply home, right? So let's do this. I have home from the w. Or maybe
Yeah,
I
you need to apply home to the y. Yeah, that's true. That's true. It's proven by that.
Yeah, but I think in the home I need to start with the x.
You need to start with the c.
No, this is contravariant factor. C will be at the very end.
No, yeah, it's contravariant, so you should start home to this from c to the y, then home from x to the y, and then home from w to the y.
Okay.
We should have the right triangle in the normal form. Then it will be easier.
So this will be what? W, right? To the y.
W to the x.
Okay, so here we have f minus g, right? So now this is just a composition with the alpha again. So this is 0. And so now this map is induced by what? So this is, if I call this, for example, phi and psi, so this is phi, so this is induced by the composition with the phi. So this is, well, there is some, again, maybe t, which lives in this form, such that this t is sent to the composition with the phi. So this will be t and phi, and this is f minus g, right? Yeah, but I think now, if I take the composition with the previous map, what I have f minus g is this composition, right? Now, and then if I have composition with the previous map, I'll get what, alpha?
Excuse me, I
No.
don't understand why f minus g goes to 0.
Because of exactness.
Here goes to 0.
Yes.
Yeah, because the baby cross. No, wait.
We just know that f
So
minus g
we
is
take-
factored through.
Yeah, yes.
We take psi in the home from C to Y. Yeah?
Yes.
There is
Yes.
psi.
Yes.
This goes to psi composed with phi. So
What's psi is from a c.
yeah, from C.
Okay.
So there you should take psi, go from it. You get psi composed with phi. So f minus j.
Yes.
That means that after that, by exactness, it goes to 0.
Mhm.
So, and we need to analyze what the map from home x y to home w y. This map is exactly recomposition with alpha.
Yes.
And that's all.
Yeah.
No, this makes sense.
Okay.
Oh, okay. So anyway, that's the end of the proof. Okay.
Okay, there is a little lemma. So the zero object, so I'm now going to the statement that D mod C is an additive category. So the zero object of D is also zero object in D mod C. Well, I'm going to leave this as an exercise. There is nothing triangulated in this proof. What's the zero object? That's an object that's initial and terminal at the same time. Well, the proofs are kind of dual to each other. You take an initial object in the D and check that this is also initial in the D mod C, and the same for the terminal. But what is a little bit more interesting to prove and requires some computation is the following. If I take two objects x and y in the category D and say that the x direct sum with y is a byproduct in D, byproduct in D, then the same direct sum is byproduct in the D mod C. Okay, so we need to show this. Well, we used to remember what the byproduct is.
Co-product is also product.
Yes. So byproduct, if you have an additive category and you have just two objects or finitely many objects, then the product and the product is the same, and that's called the byproduct. So, for example, it's enough to show that this is coproduct. So, if we show that x plus y is coproduct, and proof for the product is anonymous. Okay, so let's check the universal property. So let's take two diagrams. So with the E, T, and X, and with some E prime, map G, T, and Y. So this is alpha, this is alpha prime. So these diagrams represent maps in the quotient category. course, these diagrams, I assume that alpha and alpha prime are equal for C. So I want to show, well, these are kind of map from the X to the T, map from the Y to the T in the quotient category, and I want to show that there is a unique map from the X plus Y to the T. Now I take alpha and alpha prime, consider two corresponding distinguished triangles. So we have P alpha X sum Z, P shift by 1. The same I do for the alpha prime, P prime alpha prime, P prime alpha prime to the Y, and then there is Z prime and the shift of the P prime by 1. So here Z and Z prime are in the category C. Then I can take the sum of two triangles. And this is an exercise that will be in the first problem set to show that the sum of two triangles is a sum of two distinguished triangles is a distinguished triangle. So here I'm kind of using this without a proof. The sum is distinguished triangle. And in this distinguished triangle, of course, if two objects are in the C, then the direct sum is also in the C. So we can conclude that the direct sum of two maps is in the more C. And if this is the case, I can take object P plus P prime, the map given by the maps F and G to the T, and then the direct sum of the alpha and alpha prime. That's a map from the X plus Y. So this is a roof, right? Since this is in the morphism, this is representing some map in the D mod C. Right, so that's a map, but if I want to check that this is a coproduct, of course, it's not any map won't do it. It has to be a map that makes two triangle commutative, right? And the two triangle is just the embeddings. So I can do the following computation. Take this. Perhaps I won't rewrite this. So that's a map, and I want to take the composition of this map with the X, which is embedded by I1 into the direct sum, X1. So this is Q of I1. So let's do this computation. I have X mapped to the X plus Y. This is identity. Here I have P plus P prime, this is alpha plus alpha prime, F, G to the T. So I'm claiming that I can complete this diagram by taking object P. The vertical map is alpha, and the horizontal map is just the embedding of the P into the direct sum. So let me call this with the matrix 0, 1. So you can simplify this immediately. This will be P, which is mapped with the map F to the T, and the vertical map is alpha, which is what we need, right? And of course the computation with the I2 is more or less the same, so I'm going to skip this. So we constructed the map. So I'm going to erase this now. So we have a diagram X, Y, X plus Y. Here we have the embeddings I1 and I2. Here we have some object T. And this goes. There's a little problem, so I'm calling this maps F and G, but this is not, well, this is the maps that are represented by those two rows. So maybe something like F and G is quotation marks. So we constructed the map here, right? So we constructed the map here. We check by that computation that this composition is what we need, namely the map that is used by this roof. And the computation for I2 is the same. So I'm leaving this as an exercise. Okay. So the next step would be is to show that the map is unique, right? So suppose we have now two maps that satisfy these two commutativity relations. So uniqueness. Uniqueness of the map. Okay, so we take two maps, and now for these maps, I want to use the other kind of fractions, the left fractions. So I'm taking two maps from the x plus y to the t and representing them by the roots of the second kind.
Why is there both R?
Now this is r prime.
And this should be not psi prime but phi prime. Or just
Well, why inside actually? Yeah, I think I just moved this prime in the wrong place. Yeah. So the first step in this uniqueness proof is to show that actually I can take, so here potentially I'll get two maps, say theta and theta prime. So without loss of generality, we may assume that R is actually equal to the R prime and maps theta also coincide. So theta is equal to the theta star.
why we can assume.
I'm going to prove this.
Ah.
So the first thing I want to do is to show that we can assume this. Well, the proof is the following. I look at the following diagram. So we take x plus y by psi, for example, with r prime. So then there is t. And there is a map to the r. Here is plus y. Fine. And this is another theta. So this square is homotopy push out. So this is homotopy push out.
Why is it theta?
This is just I need to define theta. So from R and R prime, I'm going to new object n.
Yeah, but you already used theta. It's
Well, that's right. Or maybe we didn't get, so maybe this is not a good idea. Maybe I call this some alpha and alpha prime. Alpha prime. So then I want to show that I can choose alpha to be equal to alpha prime, and this alpha which is equal to the alpha prime, it will be mapped theta. So I'm replacing these two objects r prime and r by the new object n, and I'm replacing, say, map alpha by the theta and also map alpha prime by the theta. So why this is true? Why this new triangle is equivalent? Well, that's a straightforward computation. You take one proof with the r prime. So here the map is psi, and there is a map from the t, which I call alpha, and there is n, and there is theta, and there is phi prime. And the map from the r prime to the n, well, this is just a map that I have in this diagram by the homotopy push out. I don't give a name to this map. Okay? And if you why this is commutative, why these two triangles are commutative? Well, that is because this triangle is just a definition of theta. Oh, yeah.
right? So with this definition of theta, by the definition, theta is just a map from t to the n, so I can look at this like this, or I can take this composition, this is theta. And the other map, psi prime, right, which is just this composition. So the commutativity of this triangle is again just the definition of the theta prime. So more or less these two triangles are commutative by the definition, and the map from the r prime to the n here, right? So this is a map from the Morse C, because the map from the t to the r is from the Morse C.
By the way, we just construct a homotopy push out, but before this we usually construct homotopy pullback.
Well, why we do
This
this
is the same?
because now we're going to, I'm using the other kind of fractions.
Yes, it's strange,
What?
but
The
I believe that all that we prove for pullbacks is also right for push out.
Yes, well, because in the triangulated category there's no difference between pullbacks and push-outs. It's a homotopy Cartesian squares. So saying that this is homotopy push-out or saying that this is homotopy pullback is equivalent to the same existence of the same distinguished triangle. Okay, so indeed after this computation, I can work with this x plus y with the map psi prime to the n, and the map, the second map instead of alpha, this will be theta, the same will be here, but I want to return to the previous notation. So I can assume now that r is equal to the r prime and alpha is equal to the alpha prime equal to the theta. So that's an explanation why I can do this. Okay, now I have to do computation with the fractions. I have two observations. So Q of the theta inverse. I take
Sorry, we assume that alpha is equal to alpha prime to
theta.
theta, but they map to other objects.
No, I have, for example, what I have. I have, for example, this roof, right?
Yes, alpha and alpha prime they are the map from T to R, and theta is a map from T to N. Y and R are morphism.
Well, I have this roof, right? I showed you that this roof is equivalent to this one with the n and theta, right? And I can also do the same equivalent computation and say that this roof also will be equivalent where instead of the r I have n and instead of alpha I have theta. Just will be phi prime.
Okay.
So instead of r and r prime, now I'm taking n. And instead of alpha and alpha prime, I'm taking theta. But I just want to go back to my notation. So
Okay.
I prove this claim, and now I work with these two roofs with the assumption that r is equal to the r prime and maps are the same. And do the computation with the fractions. Okay, so first of all, this is supposed to be I1. So such composition is equal to the Q of the theta composition with the Q psi I1. Right? Well, that is because the phi and psi are presenting two maps here, right? And I'm just saying that I have composition of the I1 and say this map with the phi, right? So the map with the phi, again, alpha is equal to the theta, is represented by the fraction Q of theta inverse Q of phi, right? And this is so the left hand side here is precisely the composition written as a fraction. And this is of course represented by this map. And if I take the composition with the map as represented by this roof, this will be the right hand side. So this is why I have this identity, and of course I have precisely the same identity if I replace by the I1 in the computation by the I2. So there is another formula of this kind. So Q of theta inverse Q of the phi I2 is equal to the Q of theta inverse composition with the Q of the sine I2. But in the quotient category, this Q of theta is invertible, so I can just cancel it and say that the Q of the phi I1 is equal to the Q of the phi I1, and the same for the I2. Notice that at this point, when I do this computation with the fractions, maybe get familiar with this as a remark, it is important now that I work with this kind of fractions. Because if I work with the first kind of fractions, I'll get something like this. I'll get Q of phi, Q of the theta inverse, Q of the I1. So this, for example, will be analog here. Right? And this is a problem because I cannot cancel term in the middle.
Yeah, but we can prove that not x plus y is product. We can prove that it's co-product, and then this will not be the problem.
Oh, but you kind of need to prove this product in co-product.
Yeah, but then we say analogous.
Okay, anyway, so this is the reason why I do this computation with this kind of Russo fractions. Because otherwise I get this problem and I need to find a solution for this problem. And here, this everything just straightforward. So this won't work. Okay, so then the conclusion from the previous computation is that if I take, for example, the difference with the ik, where k is 1 or 2, these factors through ck, where ck is an object in the C. So k is 1 or 2. I'm just applying the lemma, right? If I know that the Q of two maps are the same, it means that the difference is factoring through the object in the category C. So we have two such factorizations. Say x is mapped to the C1 and this is mapped to the T, and y is mapped to the C2, this is mapped to the T. And for the two factorizations, I can take the sum of the diagrams, and then I'll get just the phi minus psi and factorization from the x
But
plus.
when you have the T, you should have M or R.
R, yes. So take the sum of these two diagrams. I'll have x plus y, which is mapped to the C plus C2. This is mapped to the R plus R. And this is by the codiagonal map is mapped to the R. So of course the sum of the two objects is in the category C. So we can see that the difference of these two maps again factors through the object in the category C. Hence Q of phi is the same as the Q of psi. And trivially, I can kind of precompose this with the Q theta inverse. So Q theta inverse Q phi is equal to the Q theta inverse Q psi, which indeed means that these two maps that we consider coincide. So we constructed the map, and this map is unique. And that's the end of the proof for the coproduct part, and for the product. Try to do this as an exercise. The rest of it is well.
Да-да-да, ну что
Да,
так?
полночь. Я понял, что да, то, что я сказал, это полночь, что это не так не работает. Я раз поговорил, что на поверхности, если мы возьмем, ну, то есть у нас там технологии либо блоком воды, либо через одну. Вот. Но это неправда, потому что тексты первых все еще существуют, и они все еще зацепляются. То есть, там,
да, если это есть.
да, и стоп.
Ну только не то, что вы говорите, что весь смысл казалось повести какой-то экстуарный, и все.
Если X2 только есть, то там, мне кажется, нет, там это тоже неправда, потому что если только X2 есть, то часов первых нет, это значит, что любые, у нас попарно могут идти криминологии. Ну, или это просто прямая сумма. То есть если они идут первая, то вторая криминология.
Вы говорите, что если все первые... Сейчас. Не может быть такого, что все первые изменились, а вторые не изменились.
Нет, я говорю, что когда у нас все равно это будет просто прямая сумма своих криминологий. И тексты вторые не будут.
В смысле,
существенно
что
влиять.
то же самое будет?
Ну, в смысле, тексты вторые нам не важны, если у нас нет текстов первых.
Ну, такой текст вообще был?
Нет,
Вы были вторые, что ли?
нет, понятно, бывает. Ну, взять на каком-нибудь проективную, на проективной плоскости взять какие-то там, что-нибудь, такие два пучка, что...
Не, я имею в виду вообще для всей процедуры.
Вот. На самом деле у меня есть один вопрос. Другого характера.
Категория объема.
Ну, правильно.
Это у нас все x первые, это логическая размерность, и надо все уточнить, откуда здесь.
Да. Любая короткая точка
Да.
считается простая категория. Да, такого не может быть. Да, какой вопрос?
Да. Просто там можно где-то прописать?
Ну, мне кажется, закончим, да,
Вот. Если у нас есть такая организация, нарисован, нет пучка. Вот. Это есть у нас локально свободный пучок, это у нас тотальное пространство пучка. Вот.
Называется АР.
Ну, как проективизация, только афинизация. Но это то же самое, если вы это видели, ну, вот так это еще называется.
Вот так я видел, да?
Вот, да, ну, вот.
В любом случае, это типа относительный спектр.
Ну да, это относительный спектр, да, правильно.
Симулировать равную.
Ну, это в зависимости от того, как вы хотите. Ну, можно симметрически, а можно не только симметрически. Ну, в смысле, точнее, можно двойственно, а можно не двойственно. Вот, так, собственно, первый вопрос такой. Правда же, что вот у этой вот вещи, ну, давайте назовем это какой-нибудь Y, вот эта вещь, это будет просто IA. Это будет просто pullback вот этого плюс pullback E.
Это вопрос.
Да. Ну просто он следует из этого.
Сказал, что x он над полем, да, и омега x это омега x над полем.
Да, ну понятно. Ну да, тут все над полем.
Простая формула.
Так мы производная геометрия, там все над полем.
Я локально свободен.
Ну да, я локально свободна.
Ну, что такое точно верно, да? Ну, там, наверное, можно сказать, что будет какая-то короткая точная последовательность, где у вас будет вот, как раз омега y в центре, ну и да, она расщепится. Вообще она расщепится. Что она расщепится, я не очень понимаю.
Ладно, даже если она не расщепится, у нас все равно будет верно для этого, все равно будет верно вот такая вот вещь, что это омега x тензорно на внешнюю степень. Ну там верхняя звездочка, то есть тоже верхняя звездочка, где верхнюю степень e. Даже если она не расщепится, это все равно вот здесь внешняя степень, да. Верхняя, старшая степень. Вот.
Это правда.
Вот.
Но я думаю, что мне все-таки кажется, что она не расщепится вообще. Почему она расщепится?
Ну ладно, действительно невероятно. Но мне скорее вот этот факт важен. Вот. А сейчас будет такое следствие из теоремы двойственность графа, которая, конечно, можно доказать, это несложно, но это не прям быстро. Вот, следствие... Сейчас. Следствие. То, что если у нас есть, ну вот эта вот ситуация, где гладкие, все, то у нас там нижняя звездочка, омега, тут x вот сверху. То есть тут нужно y сдвинутый на размерность y, да? Размерность y. Здесь нижняя звездочка о y. Чек тензорно на омега x сдвинутый на размерность x. Вот. И, собственно, теперь, вот зная это, мы можем там перекинуть и сказать то, что нижняя звездочка о y, чек, это просто у нас что-то вот это сократится. Да, там будет нижняя звездочка о y, тензорно на внешняя степень e, сдвинутая на n. Ну, потому что размерность y минус размерность x это n. Вот. А теперь важный момент. Говорим, что вот возьмем теперь вот так вот точку, посмотрим на слои. Слои это афинное пространство. Вот. OY на этих слоях имеет когмологии только в нулевой степени. Ну вот, OY, да, то есть имеет когмологии, значит, вот этот push-forward OY имеет нетривиальные когмологии, как комплекс, только в нулевой степени. То есть, вот это на самом деле, сейчас лучше вот это. Вот это на самом деле, это что? Это просто прямая сумма s итых e, ну там, со звездочкой или не со звездочкой, смотря как вы живете. Вот, сдвинуты в нулю. Значит, вот эта вещь, это просто прямая сумма s и e, сдвинутая в ноль. Ну, это же двойственный к вот этому почему. А двойственный это что? Это просто r хом в ox. А e мы считаем локально свободным.
Сейчас. Это ответ для всей правой части написано?
Нет, это ответ только вот для этой.
Просто куда есть детерминант вверх?
Да, я просто вот только это, ну, тут понятно, тензорно помноженный на вот это. Ну, то есть я его просто не написал, я только вот эту часть написал. Вот. А слева вот такое, просто потому что двойственное.
Ну да.
А теперь вот эта вещь сконцентрирована в нуле, вот эта вещь сконцентрирована в n. Что произошло?
Откуда там справа прикрепляем? Если мы просто push-forward точку возьмем, то есть x это точка.
Нет, потому что вот эта формула верна. Ну, так пишет. А это вроде верно для... Тут пишут для гладких. Ну вот. И вопрос, собственно, а что произошло? Почему у нас вдруг что-то сконцентрировано в нуле стало равно чему-то сконцентрированному в n? Ну, это верно, только если там это оба нули, но это вроде не должны быть оба нули.
Ну нет, здесь просто вопрос, где произошла ошибка, не нужно сдвинуть на n, видимо, в этом году.
Ну, вообще, если честно, даже если тут не сдвигать на n, вот почему вот это верно, я тоже не совсем понимаю.
Где?
Ну, вот то, что вот эта вещь равна вот такому тензорному произведению. есть даже если не сдвигать на n, это тоже непонятно, почему верно.
Почему? Это как раз...
Ну, мы тут берем двойственный,
Но ты можешь
тензорим на внешний.
векторные поля подставлять в форме. Как? Ну, ты можешь, ну, тензор у тебя спаривание есть?
Что там получается?
Здесь какие-то симметричные векторы
Симметричные.
формы.
Симметричные, вот симметричные.
Чуть нехорошо строится.
Нет.
Я не знаю, просто как бы тяжело сходу сказать, хороший. Мне кажется, основная ошибка сдвиганная n.
Ну, даже без этого. Ну, просто я тут не так много этих
Ну,
шагов
если
делаю.
мы в точке смотрим, там как бы, ну, если Verdier, то это какой-нибудь изоморфный,
Да.
вот, то есть, ну, то есть, на плане,
В этом плане я даже не понимаю, почему они замышлены без сдвига на n.
нет, ну, потому что это же одномерное пространство будет, правильно?
Что?
Ну, на точке просто одномерное пространство, какое-то, правда?
Это не одномерное пространство.
Ну, лям для энергии.
Не, ну на точке-то понятно, на точке-то проблем нет. Мы не над точкой. Мы не над точкой, мы на иксе. Над точкой я просто проверял, что у нас у вот этого нет старших производных старших производных степеней. Ну, старших производных пунктов. Потому что там старших когмологий нету. Правильное слово. Вот. Ну, да, подумай.
Сюда можно взять на точку, посмотреть, если по логике скажет.
Ну, это можно сделать, если там при определенных условиях на морфизмы, которые на самом деле здесь не выполняются, потому что это не то, что нужно. Вот есть, короче, другая теорема, которую доказали Бондл и Орлов. Для нее достаточно, чтобы вот здесь был гладкий морфизм, вот здесь был гладкий собственный морфизм, и тогда можно вот перейти вот так, это все равно, что перейти вот так.
Сейчас еще раз, какой морфизм гладкий?
Вот этот гладкий собственный. Ну, это правда. Вроде.
Что значит перейти так?
Это берется
Ну,
какой-то...
перейти так, это буквально вот взять
Производный,
ПБ.
да, необычно.
Да.
Замена базы.
Так почему это не плоская замена базы?
Потому что в плоской замене базы надо было бы, чтобы вот этот был морфизм собственным, а вот этот плоским. Что неправда. Ну просто там плоская замена базы, вот в этом случае вот этот морфизм плоский, а вот этот вот собственный, тогда можно отсюда сюда перейти, но это как бы поздравляю. С спектра К перейти на афинное пространство не сложно, наверное. Понять, что это.
Ну, можно подумать.
Ну ладно.
Я спор не вижу.
Вот эта формула прям написана.
Это формула, да.
Давайте продолжим. Ну так, чтобы не нас всего. Okay, so now we can define addition on sets of the quotient category, which is kind of standard definition, right? If you have a category in which you have byproducts, you can automatically define addition by the following formula. Well, perhaps you already know this formula, just try to remind you. So you can take the diagonal map from x to the x plus x, then here you have a map fg to the y, so this is from the coproduct, and the same for the product. So this is x mapped by the f and g to the x to the y plus y, and then we have for diagonal. So these two compositions are the same, and this we use it to define some addition on the on D plus D mod C. So it's more or less clear from the definition that this is commutative, but the fact that this is associative, you need to check. So it's a standard exercise. So this was G is associative. And so say this exercise 1. And exercise 2, well, this is will be some commutative associative operation. Of course, the zero map is just the identity for this operation. And you also need to check that any map has an inverse. Well, this is very easy. If you take any map which can be presented as a fraction of this kind, right? And I'm claiming that if you want to take, say, minus this map, then this is just fraction with the same alpha, but here you take q of the minus f. Again, very easy exercise. So again, I summarize all the discussion and say a theorem that says that D mod C is an additive category, and the functor Q is also additive, more or less by previous proposition. Okay, so now I need another lemma. So this is just follows from what we've done. So another lemma that says that if I have a map in the quotient category, so a map which represented by some roof with the maps F and G and the vertex P. So this map is invertible. If and only if there is F, so there are maps F and H, such that if we take a composition of the G and F and take a composition of the H and G, then these two maps are in the morphism.
Excuse me, what does it number? What does number?
Sorry, what?
Codiagram.
In the diagram, the
Ah, yeah, so here, yeah, this is the canonical codiagonal map.
Is it sum or difference?
Huh?
It's sum, right? Like sum.
Here in the definition,
Yes.
yeah, of course, this is definition of the sum, yes. This is a standard definition. For example, if you take any book on the abelian categories, or even book on category theory with a chapter about abelian categories, that will be a definition of the addition if you have notion of the byproduct.
But just in previous board, I thought it was difference because we considered phi minus psi in that distinguished triangle.
No, that's a different statement. No, here this is the sum. It's not, has nothing to do with that statement.
There use F twice. In the triangle, in the roof, and in the there exist.
Here?
And the roof.
Oh yeah, that's not a good idea. I need to change this to some, say, alpha. Say this is alpha. Okay, proof. Okay, so suppose that I have such maps, so F and H exists. So then I can say that if I apply functor Q to the compositions which are in the more C, then these two are invertible. So Q of HG and the Q of the GF are invertible. So these are two invertible maps, of course, in the D mod C. Right? But then
I think it's clear that the Q of G is also invertible. And finally, Q of the G, which is in decomposition with the Q alpha inverse, is also invertible. Okay. Which is, again, the last fraction is represented by this rule. So this finishes the proof in one direction. Now, let's assume, so conversely, we can assume that Q of G, Q,
Excuse me, why J is invertible?
well, this is just a computation with invertible and the elements in the invertible maps in the category, right? For example, if you know that this, of course, this Q is the Q of H and Q of G, right? So this is invertible. So the composition is invertible, and well, you can what you can do. Yeah, so you can say that the Q of H, Q of G is invertible, but it means, for example, that the Q of H is the left inverse for the G. Q of G will be the right inverse. Well, up to it will be invertible map. You can kind of take this invertible map, move it in such a way that on the other half or the other part you have just the identity. Then this composition is the left invertible to the Q of G. The same here, you'll get right invertible for the Q of G. So Q of G is invertible. It's a really kind of, I think, straightforward, boring step. I didn't want to write this. So conversely, I want to assume that this fraction is invertible, or this roof is given in invertible map. So if this is invertible, then I can say that since I already know that the Q of alpha is invertible, then this roof gives me an invertible map. So P to G, Y, no, this is X, and this is P. So it is invertible. So let's T, F, P, beta, Y. B is inverse. So then I have the following computation. I have T beta Y F B. So here I have B 1 so B G and X. Well, to complete the diagram, I can use object T, map 1 and map F. So this is clearly commutative, and this one is of course the more C. So this is what I can use to compute the composition, and this can be simplified to the T, which is mapped by the composition G and F to the Y, and this is just beta mapped from T to the Y. Okay, so I know that this is its inverse, right? So in fact this roof is equivalent to the roof that gives the identity. So let me draw the corresponding diagram. So I have T, some W in the middle. There are two maps, U and V. And this is object Y. This is object Y. So this is again Y with two identities. So this is V. This is V. This is some beta. Yeah, and this is the composition of the G and F. And now we need to use 2 out of 3 properties. So first of all, we can notice that the V is the composition. So V is the composition of the beta in U. So V beta u, right? So this is beta u. What we know that the u is in the more C, and we know that the beta is in the more C. So V is in the more C. And finally, looking at this triangle, right? So the composition is V is in more C. So this is in more C. So this map also has to be in the more C.
Why not X?
Should it be X?
Shouldn't it be inverse to the map from P to X, the map from X to P?
I don't know. I know why I switched to it. This is X everywhere, right? Yeah.
Yes.
Yeah. I don't know. In my notes and also on the blackboard, I somehow switched to Y for no reason. But the argument still works, right? So this two diagrams are equivalent. So V is in the more C, and by looking at this triangle, we can conclude that the composition GF is also in the more C. So we kind of proved the part of this. If this is invertible, we proved that there is an F such that the GF is in the more C. And there is the second half. I'm going to leave this as an exercise because the computation is the same. You just need to take this composition in the other order. To do the composition in the other order, you can write such a diagram and you'll get the second part of the statement. Okay.
So next proposition. So this next proposition is so simple, it's actually quite hard to prove. Because you go to the computation with a lot of maps which are actually zero maps. And it still makes sense and it's still useful computation. So a map G from X to a zero map in D becomes an isomorphism in the D mod C if and only if there is object Y in the D such that the direct sum of the X plus Y is in this. I think that's a very interesting statement. It says that, okay, we define this notion of a quotient category, and the intuitive meaning of this quotient would be that all the objects in the C are zero, right? But here it's a little bit more precise there. So you are interested, for example, when object X is zero in the quotient category. Well, the correct statement, if and only if, is actually a direct sum of an object in the C. So the zero objects, not just objects in the C, but all their direct sums. So this is what we see in this proposition. Okay. Proof?
It's really a bit strange why it's some C, not X.
No, we're going to show that this is correct. It's actually, well,
How intuitive it can be?
well, the answer maybe is the following. There are different ways to define quotient categories. The way I define it, I just to take a quotient of by any triangulated subcategory. For example, we have this quotient functor, so Q, this is a functor from here. And you can ask, what's the kernel of Q, right? So you would expect that the answer is C, but this is wrong. The correct answer is the thick closure of the C. So meaning that we add all the direct sums. So this is the smallest triangulated subcategory close to the direct sums that contain C. So in fact, we can say that in this theory, if you want kernel of Q to be C, you need to start not with subcategory, triangulated subcategory, but you need to start with thick triangulated category. Then everything will be correct. So then
But this follows from proposition.
Hmm?
But this follows from proposition.
Yeah, this follows from proposition. So it's saying that if you take a quotient by any intrinsic category, it exists. That's not exactly what you want. Probably, if you want kind of very nice theory, you want to take a Fichter category. Then the object is zero even in the quotient, if and only if it belongs to C.
It's like saturation and localization in primitive algebra, right?
Well, as an analogy. Yeah. Okay. Okay, so let's try to prove this in one direction. If I know that if I apply group Q to the G, I'll get an invertible map. So if this is invertible, so then by the lemma there is a map H. So I'm using lemma here that I just proved, such that x to the 0 map H to some object which I'm going to call y shifted by 1. So this is in the Morse C. So there is an H such that this composition is in Morse C. And they also have a distinguished triangle. So we can take x, 0 map to the y shifted by 1. And if I complete this distinguished triangle with the 0 map, what I get is always the sum of the x shifted by 1 plus y shifted by 1. And then the last one is just a projection. So this will be one of the exercises in the first problem sheet. What happens with the distinguished triangles if one of the maps in the distinguished triangle is 0? It says that the other two maps are actually just the embedding of a direct summand and projection to a direct summand. So for a 0, we always have such distinguished triangle. So this is distinguished triangle, and the sum of the x and y and the sum, since the 0 map is of course, 0 map is of course in the Morse C. So this composition is in Morse C, but this is of course a 0 map from the x to the y shifted by 1. We can conclude that the x shifted by 1 plus y shifted by 1 is in the C, and hence, since shift is just an autoequivalence and C is closed out under autoequivalences, x and also additive, x plus y is in the C. Right? So this is the proof in one direction. If an object becomes isomorphic in the quotient category, then this is the direct sum of some object in the C. So conversely, if I assume that the
I'm sorry, I don't understand. We have this triangle, and why 0? Why the co-kernel of 0 lie in C?
Well, I'm promise you an exercise in the first problem should, if you have a distinguished triangle in which one map is 0, and the other two maps are just the embedding and projection for direct sums. So if you try to start with the 0 map, complete this to distinguished triangle, you get distinguished triangle with this direct sum.
We know that the 0 map lie in Morse C.
By this computation.
Because the next one is 0.
No, because
because the composition.
This is the map that I used from x to the y shifted by 1.
Composition.
But this is factors through 0, so this has to be 0.
Composition is in Morse C.
Yeah.
Okay, and since shift lie in C, then
This
object
other
lies in C.
the object will also in C.
Okay.
So yeah, conversely, let's assume that this direct sum is in the C. So let's take two maps. So take H to be a map from the 0 to the y shifted by 1. Of course, this is a 0 map. I'm just giving a name for a 0 map to apply the previous lemma, right? So F is a map from the 0 to the x. Again, this is a 0 map. Now, if I take the composition G and F, that's a 0 map from the 0 object to the 0 object. Oh, this is an isomorphism. And any isomorphism is in the mod C. This whole proof is exercised in trivialities. So GF is in the mod C. Now HG, which is a map from the x to the y shifted by 1, which is still a 0 map, right, is 0. Look at the distinguished triangle with the composition H and G. X, y shifted by 1. So again, as before, this is a direct sum of the x shifted by 1 and the y shifted by 1. This is in the x shifted by 1. So this is an object in the C. Again, the same argument as before. But because x plus y is in the C, the shift is in the C, which means that Hg, this composition, is in the mod C. Right? So the conditions of the lemma are satisfied, hence this is an invertible map in the quotient category. Okay. And actually I wanted to do this definition of the thick subcategory and thick closure. So a triangulated subcategory is called thick if it is closed under direct summons. Okay. Do I need to explain what means closed under direct summons, or is it clear?
Why we need it to be triangulated subcategories?
It's just a definition.
So just category can't be so just subcategory can't be.
Well, I think in the abelian categories, for example, this is not kind of the way it is defined. It's not how the word thick is used.
Mm-hmm.
In the abelian category, you just call this a subcategory closed under direct summons. I don't think that there is a special terminology just for this. And I think thick in the abelian sense is something different, I think. I'm not completely sure, but I think it's...
This
Not-
means that some objects is equal to, for example, x plus y, then both x and y lie in the...
Exactly, yes. Okay, maybe let me say that this is first part of the definition, and second part of the definition is the following. If, for example, S in the triangulated category is a class of objects, then the thick closure of S is the smallest triangulated subcategory. Smallest thick subcategory. Containing the given class S. So, for example, what we proved before, this statement of proposition, so this is the kernel of the Q, is the, and the notation for the thick closure is thick of S. Well, there are different notations. Well, I know two. For example, there is another one, triangle. If you want to emphasize in which category you take this triangle, of the S with the bar.
So these are two notations for the thick closure. And triangle without bar is just the smallest triangle. It's a category containing the given class of objects.
So the kernel of Q is the, but I like this notation with the thick closure. It's long, but it's kind of not confusing. If you see this, you understand what it means. You can't forget what it means. For example, for this triangle with the bar, you can forget what it means. There's also another kind of closure, the localizing closure, so it might be a problem. So the kernel of Q is the thick closure of the category C. So in particular, if you start with a thick category, then everything is nice, and the kernel is exactly the category. Okay, so I want to finish this chapter
With one technical lemma, which I'm not going to apply, but this might be useful when you try to check that a quotient category is the great category. So lemma. I'm not sure how to formulate this. Okay, maybe if in the map of distinguished triangles, so we have two distinguished triangles, x, y, z, and x shifted by 1, x prime, y prime, z prime, x prime shifted by 1, and the maps are F. So let me call the first map U in the first triangle and U prime in the second triangle, and the map are F, G. Oh, and then there's potentially map H. Right? So we know it always exists. But the claim is, so if in the map of the distinguished triangles we know that F and G are in the mode C, then we can choose H in the mode C. So map H, of course, lives here. So I'm not claiming that if you have such diagram and F and G are in the mode C, then automatically H is in the mode C. I'm only claiming that you can choose such H if you work a little bit more accurately. Okay. The proof is the application of the octahedral axiom twice. You started the original diagram, you decompose this diagram into two diagrams. So take the first row the same as before. So then you take the identity on the x. So here this is map G to the y prime. And the map from the x to the y prime is just decomposition. So this is 1, and this is of course map u prime f, which is the same as the gu. So here is map f. Now this is the identity u prime, x prime. And so I decompose this triangle into the composition of, this square into the composition of two squares. And the same. Okay. So say this is shift, and this is F. So I do this decomposition, so I have this map, and I complete this map to a distinguished triangle. So now I can construct map, so I want to construct map H1 and I want to construct map H2, right? In such a way that these two maps are in the word C. Then the composition also will be in the word C, and I prove the lemma.
Okay, for the H1, I apply the octahedral axiom, right? Because now I have the kind of the right situation. I have the distinguished triangle for one map, distinguished triangle for another map, and distinguished triangle for their composition. This is what we have in the beginning of the TR4, and then by the TR4 we have the following diagram: X, U, Y, Z. I'm only going to draw part. I'm not going to do several zeros and zero maps, only a part that is important for the computation. So X, composition of the G and U, Y prime, this is Z prime, this is map H1, X shifted by 1, this is 1, Y double prime, Y with the shift, Z with the shift, okay. So we have this additional distinguished triangle that starts with the map H1. So now, so map G is here. So now we know that the G is in the morphisms, so in the morph C. So this means that Y double prime is in C. But now in this new distinguished triangle that we get by the octahedral axiom, we have the same object Y double prime, which is in the C. So the H1 is in the C. So this is the proof for the H1.
In more C.
So yeah, in more C. Thank you. So this is the proof of the first part of the diagram. Maybe I'll leave it as an exercise for the second part again.
You take the second part. It's a shifted, so we need to shift it back, but then apply the octahedral axiom, the same argument. H2 you can choose for the more C, and the composition will be
Composition will be in the more C. So for H2.
Let's shift it.
Well, in my computation it is shifted. Okay.
Normally, okay.
Well,
Yeah.
because essentially,
You have one.
yeah, you need the kind of, to apply the octahedral axiom directly. You need a diagram that starts with one here. Right, so maybe useful would be to start here and then write two terms here and do that octahedral computation with this additional square here.
okay.
Let me erase this. And finally, define a derived structure on the quotient. So, definition, D mod C is triangulated category. And distinguished triangles in the D mod C are, by definition, triangles isomorphic to triangles of the following form. You take U of X, U of Y, and then U of Z, and then U of X shifted by 1, where X, Y, and Z is a distinguished triangle in the category D. So this is how you define the distinguished triangles. And the shift functor, I think this is automatic, because objects are the same. You can do the shift in the category Z and say that this is a shift in the D mod C. And so, from the definition, it immediately follows, so clearly, the functor Q from D to D mod C is a triangulated functor. Well, because we just defined an instruction D mod C in this way. So the exercise is to check, the exercise that will be in the first problem set is to check TR0 to TR1 more in demos. Of course, really the exercise is to check TR3 and TR4. Because the actions are very easy. Okay. So that's all I want to say about the quotients. And maybe before I go to the next chapter, I say some simple things. Probably you already know this, but maybe to fix notation about the homotopy category. So maybe let's say this homotopy and derived category. So let A be abelian category. You can do this a little bit more generally. You can take an exact category, but in this case we only consider abelian category case. So then we have some notation. So C of A is the category of complexes. Right, this the standard thing. You have some A0 which is mapped to A1, So the maps are differentials. And if you take the composition of any two maps, then you get 0. That's a complex. So the objects in the CA are just such complexes, and the maps between complexes are trivial, right? So this is just a bunch of maps such that every square is commutative. And it's easy to see that the C of A is abelian. You can take kernels and kernels and images kind of term-wise. And for this category, there are variations. So, for example, there is C minus of A. Maybe I explain this once, and the same will be for homotopy and derived category. So this is complexes bounded above. There is C plus of A. So these are complexes bounded below. And CB, these are just bounded complexes. Right. So bounded above means that after some term, all you have is just zeros, zero objects and zero maps. Bounded below means again that going to the negative direction, at some point you have zeros, and after this you get just all objects and all maps are zeros. And bound complexes, it just means that it lives in some bounded from some one integer to another integer, and after this integers everything is 0. Okay. For the homotopy category, so homotopy category of A. So the notation for the homotopy category, there are two notations. The standard is K of A and H of A. I'm not completely sure, but I have a feeling that this K of A is maybe from the German, maybe from the French for the homotopy, and H is just for the homotopy of A. So what's the definition? The objects are the same. So objects of the K of A is the same as the objects in the category of the complexes of A. We are changing the homes. So the home in the homotopy category, you can define it, for example, between two complexes x and y. So we can define this as a zeros homology of the complex, which is usually called home with a dot. So this is home complex between two complexes. So home with a dot between two complexes x and y. So this is a Hom complex, and this is by definition the product over all integers of the Homs of degree I from the x to the y. So with the differential, which I'm going to call large D, so differential of the map is the f composition with the d differential of the complex x minus of the correct sign, so minus 1 to the I of the differential y. So here, writing this formula, I assume that f is in the form I x1. So between complexes, I can consider Homs of degree 0. So, for example, we map from the A0 to B0, A1 to B1. These are maps in this C, and this is just an abelian group. But you can also consider maps of all possible degrees, right? So we can go from A0 to B1, that will be from A1 to B2, so increasing degree by 1, that will be a map of degree 1. And in this Hom complex, you combine everything, and there is this canonical differential. Of course, it is very easy to see with this exercise that the d squared is 0, and you take the zeroth homology of this Hom complex, and you say that this is by definition Homs in the homotopy category. If you know another definition of when in terms of formulas, you can say that a map is homotopic to 0 if there is such a formula. Remember, there will be such a differential. So map is homotopic to 0. So f is homotopic to 0. This means that f is the d of some h, and the degree of this h is minus 1. So h is in the Hom minus 1 xy. So meaning that instead of this minuses, you'll get plus. Perhaps you've seen such definition, but you see that this is exactly equivalent to this definition. When you compute the homology, first of all, you take the kernel of the differential. So the kernel of this differential is exactly maps that commute to the differential modulo the d of h, where h is of degree minus 1. So the standard homotopy relation. So that's a homotopy category, and about this homotopy category, well, you can define, of course, k with a star, a where the star is minus, plus, or bounded. The same definition, just instead of the c of a, you take the corresponding c with the symbol. And the exercise that, maybe another big exercise in the first problem set, is to show that the homotopy category of K is triangulated category. Yeah, it's not very hard, but maybe I'll do part of this exercise. I define the distinguished triangles. So we have a notion of a cone, so suppose we have f, a map from the x to the y. So this is a map of complexes. So the mapping cone of f is notation is c of f, and if I want term in degree I, so this is by definition x in degree I plus 1 plus y in degree I. So we can say that without the differential, the complex is just the shift of the complex x plus y. Yeah, by the way, the shift by 1, if I want degree I, so this is the x in the I plus 1. This is the definition. Well, of course, with the minus 1, the same definition, I minus 1. So, and this cone has a differential, so the differential in the column of the morphism, well, since this is kind of sum of two objects, we can write the differential as a 2 by 2 matrix. I plus 1x, 0, f I plus 1, dy I.
Okay, so why this colon is useful? Well, for example, for any such map F, you always have a short exact sequence in the category of complexes. So 0, y, colon, and then x shifted by 1. You can check this by looking at the, well, essentially because you have 0 in the colon, it means exactly that y is a sub-object, and if you take a quotient by the y, you get x shifted by 1. So that's essentially the proof. So, for example, F is quasi-isomorphism if and only if the colon is acyclic. Right? You just take this short exact sequence of complex, look at the long exact sequence of the homology, and F will induce isomorphism of homology if and only if the homology of this last term C of F is 0. Okay. So this one I need to define distinguished triangle. So distinguished triangle in the homotopy category is a triangle isomorphic to triangle X, F, Y, C of F, and then the map X shifted by 1. So in the homotopy category, you see that the completion of the cone that we should have is just taking off the the completion of the map to a distinguished triangle, just taking the cone of this map. This is why sometimes even if you work with abstract and related categories, you call the third object the cone of this map. But this is just the abuse of notation. Okay, so with this definition of the distinguished triangle, you need to check that homotopy category is triangulated category. Again, the first reactions are trivial, and the real pain is the last one. So finally, we can define AC of A. So this is a triangulated subcategory of the K of A. So full triangulated subcategory of acyclic complexes. And by definition, the derived category is the quotient of the homotopy category by the subcategory of acyclic complexes. So this is how we already know what the quotient category for triangulated categories is, so this definition now makes sense. And we don't need separately to check that this is a triangulated category. This kind of follows from our knowledge about that this is triangulated category, and any quotient is triangulated category. Okay, so I have some other information about derived categories, but maybe I'll avoid doing this exercises in the first problem sheet. Okay. So let me start a new chapter. Yeah, I've done this because we discussed the abstract theory of triangulated categories, and here are some explicit examples. Actually, this is the most interesting examples for us. For us, maybe almost all triangulated categories that we're going to consider are the derived categories of some abelian categories. Okay, so chapter 3. Localizing subcategories. Well, there will be more than just localizing subcategories in this chapter. So let me separate this into several sections. So the first section will be indeed about definition and properties of localizing subcategories.
start with the definition, of course. So first, well, maybe I even need to write also call in the name of the chapter. There's a localizing subcategory, there's co-localizing subcategory, and this kind of dual to each other theories. So first of all, in the definition, in the first part, I assume that I have triangulated category, so let T be a triangulated category with all small co-products. So then, the triangulated category, triangulated subcategory L of T is called localizing. If it is closed, under coproducts. And the second part of the definition is dual, so L in T is co-localizing. If it is closed, under products. So of course in the second case, assuming that T has all small products, but I just don't want to write this. Okay. And there is also, as before, the localizing closure, so loc S, so this is localizing closure of a class of objects S. So this again, it's the smallest triangulated localizing subcategory containing the given class S. And there is a co-localizing closure. But mostly we will be interested in the localizing subcategories and localizing closures. And well, I have another definition, which I want to give in the very beginning, about the right and left orthogonal. So first, we can take S to be a class of objects. You can take this to be a subcategory, but objects are what important in this subcategory. So then the S right orthogonal, this is by definition, well, this is the full subcategory of all the objects in triangulated category such that the home from Y to X is 0 for any Y in the S. This is kind of the standard abuse of notation. I'm writing this as a set, but what I mean by this is the full subcategory with such objects. So this is full triangulated subcategory. With objects given by this condition. Well, maybe I need to write one here for the definition of the right orthogonal. There is also definition of the left orthogonal. So two left orthogonal.
So it doesn't matter if you asked the localizing subcategory to be closed under coproducts or small products.
Well, by small I mean that we take coproducts over sets.
And then we say that this is closed under coproducts. It doesn't matter if it's
Yes, small coproducts. Yes, small. All products and co-products, our limits and quantities are small. Yes, so for the left orthogonal, these are all objects such that the home.
What does this mean? What does it mean small products?
Sorry, what?
What does it mean small products?
Oversets. Oversets. So if you have any set of objects, you have a product. This is to distinguish with the products or co-products over classes.
which I don't require to exist, because actually if you require in the category such things, it means that it's very small category,
And when
very restricted.
in the second part, we also need tau to be resolved.
Yeah, so here to make sense of this definition, I assume that in the T I have all small products, and the category L is closed under these small products. I just didn't want to repeat this whole sentence for the part 2.
This is not the. Sorry, I think there should be a shift. So whole from Y to X to arrow shifts.
Yeah, maybe you're right.
Since we doesn't say
Yeah,
that
if
S is
if I say this is triangulated subcategory, I don't need this, but if this is just a class, I need to add the shift. Yes, thank you. So shift by k, and this is for any k which is integer. So this is for any y in the S, and any k integer number. Again, what I meant by this orthogonal is that I consider the full subcategory with such objects. Yes. So, and there's another terminology that the objects of L, sorry, of the S with the right orthogonal are called as local, and the objects of the left orthogonal are called as just terminology. Sometimes I'm going to use this terminology. Okay.
Okay, so cross proposition. So let me take S in the T be triangulated subcategory. So then I have two solutions. So first, the left orthogonal to the S is localizing. And the right orthogonal to the S is localizing. So again, I don't say this, but I assume that whenever I talk about the localizing, I assume that in T I have all the small co-products. And for localizing, I have all small products. This is the assumption. Without this assumption, it doesn't even make sense to talk about these objects, subcategories. Okay, so of course the proofs are more or less the same, so it's not to prove only one of these two statements, so I'm going to prove two. Okay, so what is clear? So clearly, right orthogonal is additive and replete. Right. So
And this is mean that
closed and isomorphisms. If the object size is 1, if it's 1 from the 0, also 0. So then if I take an object X in the right orthogonal and take object Y in the S, so then on all the Y and X shifted by 1.
isomorphic to the home between y shifted by -1 and x. So, since we have this definition for all the shifts, I can conclude that S right orthogonal is closed under shifts by plus or minus 1 or by any integer. Okay, so this is closed under the shifts. Now we need to check that this is a triangulated category, right? So we need to check the property that if you have a distinguished triangle, so x, y, z, x, and the shift is a distinguished triangle. Distinguished triangle with the x and y into the S right orthogonal. So applying from the object S, where this object S lives in the category S, we get long exact sequence, and from this long exact sequence we can say that the home between S and Z is 0. So this is for any real S in the category S. So Z is also in the right orthogonal. So now this is triangulated category, but to check that this is co-localizing, it's actually not harder if you take the product, then we know that the product commutes with the home, so this will be the product of the homes. And this is 0, right? So this is if yi are all in the S, and sorry, in the S right orthogonal, and x is in the S. So we check all the conditions because the first one is the same as the trivial proof. Okay, next. So proposition that if
I suppose there should be if not my I.
Okay, so if C in D is localizing, then D mod C has all small coproducts and the quotient functor from D to the D mod C preserves coproducts. Okay. In the proof, let me fix notation for a coproduct in D. So let me say that I have xi, and then the canonical injections are ui to the coproduct of the xi. So this is diagram for the coproduct in D. So let fi from the xi to the y be maps in the quotient category, so represented by some roots. Represented by the roots, we'll have some wi map alpha I from the more C to the xi, and y with the map beta I. So alpha I is in the more C. So So for this rows, we can take a coproduct, right? So then we'll get the direct sum of the xi, the direct sum of all the maps alpha I, and direct sum of the omega I. Okay, so I want to say that the direct sum of the alpha I is in the Morse C. So do you see how to prove that direct sum of the morphisms is in the Morse C?
Because all non-direct sums is the direct sum. So we just take the distinguished triangles and direct sum them.
Yeah. So this follows from the fact that any direct sum of distinguished triangles is a distinguished triangle. We've used this before for 2, but this is the same proof shows that this works for any set of distinguished triangles. And in this, if you take distinguished triangles like this, you have Wi map alpha I to the xi, or there is something else, some maybe ci. Right, you take a sum of all such things. And you use the fact that this direct sum of Ci's is also an object in the C. This is because we assume that the category C is localizing, and hence this direct sum is a map in the Morse C. Okay, so we constructed now a map in the, so this roof is representing a map from the direct sum of the xi to the y in the D mod C. So let's call this map maybe F, and then by the construction you can immediately check that if you take composition of the x and the f and the q applied to the ui, then you'll get the fi. So check this. Now, so we constructed the map, and now we need to check that this map is unique. So uniqueness, if f from the direct sum of the xi to the y in D mod C satisfies f composition with the q of ui is 0, I want to show that this map f is 0. So let me again represent this by the roof of the second kind. So I have direct sum of the xi, there is a map A to some w, y, and there is a map b, and I assume that this map b is in the Morse C. So by this presentation, it means that I can write f as the q of b inverse, composition with the q of a, so the left fraction. Now, since composition of the f and the q of ui is 0, I can take the composition of this on the left and on the right with this q ui. Since q of b is invertible, I can conclude that q of the a ui
ui is 0. So this means that this map a ui factors, not what we proved before, factors to an object in C. Through some Ci, it's object in C. So then, if you have this for each component, then the map A factors through there is some of such CIs in this, again, this object in the C, because the subcategory is localizing. And using this lemma in other direction, we conclude that the Q of A is 0, hence lemma F is 0, hence such map is unique. And functor Q preserves for product, this is more or less by the definition. Okay. Yeah, think about it. So that's all I want to say for today, and we continue next time. So far everything has, I think this was more or less just boring and more or less automatic. There will be interesting theorems, but maybe next time, but at some point there will be interesting theorems.
Can you give examples of that?
Hmm?
Can you give examples of this interesting theorems?
Да нет, вот просто проблема в том, что сейчас вот все эти вычисления нужно проделать самому, и все. Сейчас идут такие вычисления, которые нужно просто проделать самому, чтобы понять.
Похоже, честно. Мне кажется, единственное нейтральное утверждение, которое доказало то, что это аддитивная категория, для паса аддитивная категория. Там понадобится как бы дроби другого сорта, это не значит, что надо использовать другого сорта, может там запутаться. А все остальное действительно нужно ставить, конечно, упражнение.
Это так, конечно, такое. Почему тут постоянно корень меняется? То есть, во-первых, я не совсем понимаю, почему у нас S правый ортогонал, это S local объект. Ну, то есть объект оттуда называется S локальный, при условии того, что правый ортогонал колокальный.
Ну, это то же самое, что и
Колокализирован.
Почему?
У нас локализующая
Да.
категория знаходится на колокализировании.
Это неправильно.
Ну, так сложно.
Прямой предел является сколько-делом, это тоже неправильно.
Да.
Мы с этим как-то живем.
Ну не знаю, ну просто теория как будто вот изначально такое делалось неправильно.
Мне вот интересно, который я кажу, ну вот, возможно, это теория Босфорда.
Какая теория?
Босфорда. Вот это, в общем, теория про то, что можно локализовывать, есть локализация Verdier, есть локализация Босфорда. Босфорда чуть-чуть больше, как у нас потребуется данных, потребуется, чтобы вот этот микроканонический функтор имел право сопряжения. Вот, и тогда там многие условия планеты, они, например, эквивалентны к тому, что категория привела к какой-то локализации. Локализация — это функтор, который в квадрате равен самому себе. Но таких примеров довольно мало. Приходящихся в память технологии присудили. Вот, это... Ну, будет некоторая серия как бы, по утверждению средней сложности, по компактно порожденной категории. Самое главное, с которой это будет взаимопредставление сигналом, но теорема о том, что полная производная категория или какие-то категории образует множество, тоже довольно интересно. Ну, а то, что это неверно в производной категории, есть какой-то верный, если хотите, просто явно сказать, что это неверно. Ну, а потом после этого будет говорить, что геометрия.
Я правильно понимаю, что это утверждение, оно самое верно всегда, когда мы смотрим не только перебываем контекст, у нас просто есть какая-нибудь локализация, там, скажем, полной категории, то факт тоже будет полный и функция будет непрерывной.
Да, это верно. Да, вообще, кстати, я конечно, создал впечатление, что это какая-то вот локализация, какая-то категория для определенной категории. Если вы, например, захотите через табель категорию, то же самое есть. Там есть понятие фактора категории, масса категории, там есть понятие локализующей категории и все такое прочее. Поэтому это не исключительно теория для определенной категории. Есть в каком смысле делать, как проще и поудобнее. Но для определенной категории проще, чем макровой категории. Поэтому теория попроще получается.
Все-таки есть локализующие акции. Понятно.
Спасибо.
Можно, собственно, локализовать потом?
в этом смысле все единственное, по определению производной категории, по определению локализация монотопической категории.
Не, ну это один пример. Мы будем производить категории какие-то? Вот категория.
Что это значит? Если рассматривать примеры?
Ну, например, да. Я не знаю.
Нет, здесь интересно, когда выслушать магазин, выслушать преобразованную категорию. Поэтому основной ответ у нас вообще всяких примеров факторов категории можно много интересно. Категория особенностей.
Категория особенностей.
Ну, это как, ну, например, берете локальную информацию, которая не является сингулярной, то есть это какая-то локальная информация особенность, да? Берете, например, ДБ от клиента пушков особенности. А внутри, например, двух совершенно комплекции. Это конечная комплекция векторных условий. Это некоторые транзиентные условия, они можно характеризовать. И, ну, это получается некоторые тоже транзиентные условия. Ну, например, если у вас не особенность, это регулярная процесс, это почему? Это может быть сфера, что сюда а если это особенность, то это как бы категория, которая какую-то информацию про особенность. В случае, если это двигает поверхность, это маточной факторизации, если там особенность Эйнштейна, ну, там есть, например, двойственность серра, функтора, можно делать явную чтение, строить отображение. То есть, когда мы такие примеры есть, и конечно, есть даже всякая теория, но это не то, что мы будем заниматься регулярным курсом. На курсе мы всегда учимся, грубо говоря, регулярным категориям, получить новые, спать клиентам новые. Это основной пример. Хорошо. But everything to the last was spoken.
And the author can consider
Well, I recommended some books already in the first lecture. There is a, well, maybe you can just look at the beginning of the video of the previous lecture. I recommended several books.
I'm interested in like category theory and logical algebra and also like numerical algebra as well. So since I'm in the second year of master's degree, is it possible for you to be my supervisor?
Unfortunately, it's not possible. I already have several students. I just don't have enough time to be supervised. Sorry.
Одна из курсов все равно.
Yes. So you are in the first year of master's?